in particular in this theorem you can take L1 which has log n dimensions. In general, when you consider embeddings into into L1, you can always think that the number of dimensions is at most n choose 2 if you embed n points into L1 space. But it's not very important. So since we don't know what we can do with an arbitrary metric space, just let's try to do something very strange, arbitrary thing.
So now you're proving this theorem.
Yeah.
Yeah?
Let little l be logarithm of n rounded, the theorem of the logarithm of n, and let's do the following thing for each scale. So I will explain this meaning later. For each scale, consider let I be the scale 1 to L. We construct set A. And this will be this set.
AI.
It will be almost AI. So it will be a random set actually. So we construct a random set. So let's independently add points to the set, and let's add every point to A with probability 1 over 2 to the power of I.
So if you are unlikely, it can be an empty set. If you are unlikely, it can be an
It can be an actual set, right?
Maybe indeed to write AI, because there was index there and it would be.
And what do you mean for every point x? X is thrown from what?
No, for every x is not a random point. So you this set contains every point with probability 1 over 2 to the
Every point of what?
Of the
Metric space.
Of the metric space. For every point.
But it is infinite.
No, n points.
From the initial set.
Yeah.
Which is m. Okay.
And this randomness has nothing to do with the omega randomness.
It will be.
Okay. Okay.
It's not
It will be.
coincidence.
Yeah.
And now the definition of this random variable is very simple. So for every x, to every x, we just map to the random variable, which is equal to the distance from x to this random set.
A or AI?
So let me.
Does this A has a subindex?
Yeah. Let's do the following. Let's actually remove this index I, but rather say that pick I randomly from 1 to L.
Uniformly.
Randomly and uniformly, yeah. So this set A depends on two choices, the choice of I and then on these random choices for every element. Let's prove that the distortion of this map is small, is at most log n. First of all, similar to that theorem, it doesn't increase the distances. So the distance, say we map x to c, we map y to eta, then the distance between c and eta is equal to this fact expectation of the difference between distance of x to a and distance of y to a. And this distance is always at most the distance between x and y.
And so now we need to show that for a random set, the difference between distances is not very small normally, yeah?
Yeah.
It's other direction now.
Right. So we need to prove that direction. It's a little bit harder than this direction. And let's write. So we want.
But shouldn't here should be a prime for the second one? Because
No,
we
because-
probably
No,
choose
it's important that we pick the same A
for all.
for all of them. So
Oh, I see.
these choices are not. So we pick I, which is all for all elements,
Oh, I see.
and we
Okay.
so like for every A, we have its own coordinate.
Okay.
So this difference let's write it as follows. So maybe I write in the table over the probability space. Okay, I'll write now the formula, then ask whether it's obvious or not. So let's integrate from 0 to infinity.
Expected credit.
Sorry?
E.
Oh, thank you. And here probability that t lies between c and eta. So the probability that either c is less than t and less than eta, or f is less than t and less than c.
Sort of obvious. I'm joking.
Sorry?
I don't know how to prove it.
Okay. Okay. Let's write this as follows. So it's expectation.
No, just explain what is happening. T is probability is taken over what?
Over our probability space, like for everything. Over I and the set. And this formula is I mean, it's true in general. It doesn't use anything about our construction.
Yeah, so for a given value of t, you compute the probability that t separates c and
C and
eta.
that, yeah.
And then you get a number,
Yeah.
and this number is integrated over
T.
over t. So
Yeah.
if you change the order of integration
Yeah.
for each c and eta, you just integrate along T.
Yeah.
And you get this
So is it true
absolute
for
value.
Yeah.
Yeah. It has nothing to do with embedding of
Is
metric
anything
space.
about-
Yes,
Is it
yes,
true for
well,
all the
Just change the
random
order of
variables,
integration.
Yeah,
right?
let me write it.
Your argument suggests that you should put 1/2? No.
And because you have absolute value, no.
Okay,
Oh,
I think we can assume
yeah,
it's clear, because it won't make clear if you write anything else. So, if
So
it's,
this is on just the change of order of integration.
yeah.
Here at first we integrate over the probability measure, and here the difference between C and at is just the integral from C and at of 1. And here we have a first integration over T, and then integration over the probability space.
Yeah, now it's clear.
Okay. Now we want to analyze this event. Actually, let's denote the distance between x and y. So recall that x is mapped to C and y is mapped to eta. Let delta be the distance between x and y. And let's actually write a trivial bound that this quantity, this expectation, is greater than or equal just than part of this integral 0 to delta over 2 probability of the same event. Now we want to estimate this probability for every t between the 0 and delta over 2. Let's look at our points x and y. And consider balls of radius t around them. Note that since t is at most delta over 2, these two balls don't intersect. We want to estimate the probability that actually one of them doesn't contain any points from A and the other one has at least one point from A. Let's assume that this ball is larger. Say that it doesn't matter which of them is large, but let's just without local generality assume that the first ball contains more points. And say that this number of points is at most 2 to the power of I. So since this is a larger ball, the second one contains also at most 2 to the power of 5 points, and this contains more than 2 to the power of I minus 1 point, right? Look at two events. So the first event is that this larger ball intersects with A, intersects A. And actually, so at this step, we choose this parameter I randomly and uniformly between 1 and L. Note that this I also lies between 1 and L. And let's actually look what happens when this I is equal to this I. So let's look at this event conditioned on the fact that I is equal to this I.
And then we just divide by over L.
And then we will divide over L, so
Yeah.
we will multiply it by this 1 over L, and actually this is the reason why we get this log n factor, because we have log n different scales. So what does it mean? This means that we picked at least one of these points, and the probability of this event.
Maybe these scales should be complementary. So something like that the right guess is not I but n minus I, log n minus I.
No.
Okay. Okay.
So this probability is 1 over 2 to the power of I. This is the probability that we pick at the point 2 to the power of 2 I minus 1. This is a bound, and this is at least, and this is roughly 1 over E, so this is not too small number. So this is, at least with this probability, this event happens, conditioned on the fact that we correctly chose I. Now, what's the probability that this ball is empty? This event happens when we don't
Assume that the balls are exactly the same size. Then the second probability is just
No,
one minus
they
the
should be
first one,
complementary.
right?
Yeah.
They should be complementary because the chance, if you choose the random set A, the probability to hit this the ball is 1 over cardinality of A. It's not proportional to size of A. It's inversely proportional.
I mean,
A is random. It
Yes,
just
I know this.
so
Okay.
this formula, I need this formula.
Yes, it's okay. I mean, just no, okay. We discussed it in the break.
But I wonder, you want to prove that with high probability, two events happen, that t is less than eta and greater than x.
Right.
If the balls are identical, that the one of them is just 1 minus the other of them.
Yeah.
How on earth you can deduce from that that
Actually, we chose parameters so that both of them happen with a probability which is strictly below, between 0 and 1. So roughly both of them are around half.
Okay.
Therefore, and they're independent, so this will be some constant.
why they are independent?
Because
I-
the balls are not disjoint, so the
Yeah.
choice of A inside one and inside other one are independent.
At least they're independent given I.
Why they are independent? Say again.
Because
Both are
each
disjoint.
point is selected
Yeah.
with some probability, and since the balls are disjoint, the selection in one ball is independent from selection in other balls. So whether we have chosen something in one ball doesn't.
Okay. I see.
Okay, just finish the computation. Probably at that point everybody will understand.
So this probability is roughly 1 over E. So actually, at least 1 over 4. So the probability that both these two events happen is greater than some constant, which is the product of these two constants. And we get that, but yes, Sasha explained, these two events are independent, so both of them happen. So, but when this event happens, then of course the distance from X to A doesn't exceed T. When this event happens, then the distance from Y to A is greater than T. Right? So, with a constant probability, given that we get the correct value of I, this event happens. Therefore, this probability is at least 1 over log n times some constant. And we have here integration from 0 to delta over 2. So this expression is at least delta times constant over log n. And delta is the distance between x and y. So we concluded that maximum contraction is at most some constant times log n. And therefore the distortion of this embedding is big O of log n.
So is it clear now?
Any questions about this proof?
I had the problem because I thought that x and y are from A and the points are taken independent from everywhere. But actually
Okay.
x and y are arbitrary points,
Yeah.
but the points in A are fixed, so to say. In advance.
But this gives very large probability space. So we have no bound for the at least now for the.
So yeah, if you do this accurately, you can get log n, the number of, you can get log n dimensions. Moreover, the same proof, exactly the same proof, allows you to embed geometric space into L2, and in L2 you can decrease the number of them. You can always decrease the number of dimensions to log n. But
I understood it
To log n.
big O of log n in L2.
But I understood that this is very simple. I mean, the probabilistic space just is finite here.
Yeah, it's fine.
So,
No, but you need first you choose something in the I, and then you divide the space in parts, and then for each part you have some rather large cases whether everything is chosen, each point is chosen or not. So the space is more or less of size 2 to the n than log n. Yeah. If we don't do anything special.
So it's not actually hard to make a more careful analysis, but I think this is much more intuitive. So
Yeah.
this
No,
is
just a way to understand to check whether we understand correctly of the proof.
Yeah.
Whether
but so I have understood incorrectly then.
Yeah.
I thought that we just pick I, a finite number of possibilities, and then each point in A is picked or picked not, also
Independently.
two possibilities for
Yeah.
each point, and we multiply.
Yeah, so the size of the space is, first we take
L.
which is mean L parts of the
Yeah.
space, and then each part is divided to 2 to the n parts, saying which points of A are selected and which are
Okay.
not. So the total amount of points is L times 2 to the n.
Yeah, this is finite.
This is fine.
Okay,
Yeah.
and then
But it's very large, and what Yury says that if you are careful and not want to economize, you can do this. But
You
it's
can-
not important for now.
Okay.
This is the theory.
yeah.
Yeah.
So that always you can do n choose 2 just if you have any embedding in L1, but in particular in this case you can get log n.
Mhm.
I don't. So
So
how much time do I have, and whether I can use the time of the next talk?
I think
no,
you
you about 10 minutes for this.
but you should, yeah. About the next talk, probably you should call your brother whether he allows you to make this trade-off, but we cannot say this.
So finally, I want to talk about application of this theorem to the theory of approximation algorithms. So